Welcome back from the break, Matrix. Thank you so much for joining us. If you've just tuned in, we are doing your exam guide to help you prep for the upcoming exam. And like I said, guys, we've got a competition. So if you're someone who's constantly running out of data and you can't go online to check any of the content that we've created for you, this next competition is just for you. Waza Matrix is bringing you #WazaWinner competition, where 2 Matrix stand a chance to win 2 gigs of data. I'll give you all of the details on the screen and head on over to our Facebook page to take part in the competition. So enough talking from me, over to Temba.
Now, a brief look into the exam strategy in terms of, responding to different questions, right? Now, you need to learn your definitions very well. Now, definitions, they form a major proportion of, more than 30% of the marks in the total of 150. The definitions need to be extracted from the exam guidelines, okay? So the exam guideline is the most important tool for us to understand our definition. So these keywords that are in definitions, you may highlight them, but what is also important is that with definitions is either you get 2 out of 2 or 0 out of 2, right? In this case, just to emphasize on that, the keywords in the most important definitions need to be captured and be used in the correct context. What that simply means is that if you write a definition, it should make scientific sense. Not only do you have the keywords, put in the definition, but they must be in the right place to convey the correct scientific meaning. All right. And then also the data sheet is one of the very important tools that you need to familiarize yourselves with. Most of the laws, concepts are captured in the data sheet, mathematically that is. So the examiner would say define in words. Let's say for argument's sake, P is equals to mv. And when you define linear momentum of an object, it's actually the product of mass and velocity of an object. And if you look at the mathematical, formula or equation, it captures that on the right-hand side. So the data sheet is a valuable, resource in terms of remembering these definitions. We also need to pay careful attention to the mark allocation. Okay? So if a question, say, for argument's sake, is based on a calculation, and let's say it's 3 marks, it means it's a routine calculation. So routine calculation, what exactly does it involve? It involves identifying the correct formula, right? Identify the correct formula, right? So this formula needs to be copied as it is from the data sheet. Okay, there's no need whatsoever for you to try and change the subject, because in the process a lot can happen. But and please don't waste time. You don't have to do that. You just copy the formula as it is given, and marks will actually be credited for identifying the correct formula. And then when it comes to substitution, right? Pay careful attention, grade 12s, to the fact that some of the values of the quantities that are given that you need for the substitution may not necessarily be in SI units. So the SI unit is what you substitute into the equation. So if there is a need, where necessary, you need to do the conversions, say for argument's sake, from microcoulombs to coulombs, okay, milliamperes to amperes. These are just some of the examples that come to mind. And then the most important one, the free body diagrams. When you talk of the free body diagrams, you'd remember that most of all these mechanics questions are based on forces. Okay, we've mentioned linear momentum and impulse, work, energy, and power, vertical projectile motion, Newton's laws. It has to do with the forces. And even electrostatics, we talk about, electrostatic force exerted by one point charge on another. It's all about the forces. So forces are essentially vectors. So what's so important about vectors, as we would recall it from our grade 10, is that vectors have got a component of direction, something which is often, overlooked, and you'll be penalized at the end of the year if you don't pay careful attention to the vector nature of the forces. So when you draw free body diagrams, you need to indicate the forces, label them correct, make sure that the tail touches the dot, okay? But more importantly, there is a distinction or difference between a free body diagram and a force diagram. And the examiner will be very, very specific in that case to say, in this question, you are required to draw a free body diagram or just a vector diagram. So that's something that we need to definitely visit. All right. Okay. Now let's look at a typical, topic which is often also a problem, but with our emphasis on this topic, it's actually on some of the strategies, as an example. Vertical projectile motion, okay? What is important about VPM? Okay, we would summarize it as VPM, okay, which stands for vertical projectile motion. Now, the definitions, as we have indicated in the previous slide, that are very important. So what's so important about our direction is that a lot of quantities involved in vertical projectile motion are actually vectors. That's your acceleration, that's your velocity, that's your change of position, which is your displacement. Usually, if we say vertical, we'll obviously talk about delta Y, okay? So take note of that as well. But the main idea behind free-falling objects or vertical projectile motion is that there is a constant acceleration that is experienced by the object. So, I would use this statement just to capture exactly what is important about free fall and projectile, because those are the two very important terms that are most likely to be asked to define in terms of definition. Okay, a projectile is an object, right? And then free fall is a type of motion. So maybe just to summarize that, we would say a projectile undergoes free fall. Now, this is an object which undergoes free fall in the sense that only the force of gravity. Now, speaking of force of gravity, now there is a difference, again, matrix, between gravity and force of gravity, all right? One is a consequence of the other, okay? So if you think of it in terms of, the universal gravitation, the Earth tends to pull objects towards its center. So the force exerted by the center of the Earth on the object is the force of gravity. That is due to gravity. That's why the object accelerates vertically downwards. All right. Now, sketching a free body diagram for a free-falling object. Now, one of the things that we must also indicate is that as far as free fall is concerned, by the virtue of the fact that the only force acting on the object during free fall is the force of gravity, not G, is the force of gravity. Sometimes we describe it in terms of the weight, right? Now, this is the only force. So the number of marks that are allocated for the free body diagram is also an indication of the number of forces that you actually have to indicate, right? Now, the context of questions are very different. So every scenario is unique in its own special way. So read the information carefully and identify what is given. So collect the data, right? While doing so, take note of the direction, right? Because as far as direction is concerned, because these are vectors, so it has got far-reaching implications in terms of calculations, okay? Now, you also need to identify the correct equation of motion. This is also provided in the data sheet, all right? And then make sure that you understand and state or define your direction from the onset. Say, for argument's sake, if you say take upwards as positive, you're going to maintain that throughout the entire long question. So you don't change every now and again. You become consistent. So if you, for argument's sake, you throw an object up, we'll look at a particular example like that in the next slide, okay? Make sure that you immediately say, if you say upwards is positive, meaning your acceleration will be negative, which is downwards, okay? Now, also revise graphs of motion for a projectile. So these are different scenarios. It can be an object released, thrown, dropped, pay careful attention to the words because they've got scientific implications in terms of what exactly happens as far as that particular motion is concerned. All right, okay, right. These are some of the common errors that are involved as far as vertical projectile motion. We need to guard against that because marks can be lost in that way. Now, define the terms correctly, okay? Also, in referring to the force that acts on the projectile, which is the force of gravity, we've mentioned that we are not going to use the word gravity we would use the force of gravity or alternatively weight, because the two terms can be used interchangeably to refer to one and the same thing, okay? So in calculations, some candidates, they continue to say acceleration is 0 at the highest position, right? The main thing that we've also indicated as far as free fall is that the acceleration remains constant in both magnitude as well as direction. So there is no way that acceleration will change from 9.8 meters per second squared downwards to 0. So if we say it's constant, it means it does not change. Okay, that's the big idea in as far as vertical projectile motion is concerned. Okay, now the use of signs to indicate direction is one of the problem areas. Okay, so you define your direction, you choose your direction, you state it clear from the onset, and you maintain that. Okay, right. So while substitution is being carried out, take note that in physics, the negative suggests the opposite of the direction that we chose as positive from the onset. So there is no way we are saying that minus 5 meters per second is slower than 5 meters per second. It's equal magnitude, however, in opposite directions. Right. And then in the case of an object that is, say, for argument's sake, thrown vertically upwards, right, and that object reaches the highest position, this is just a scenario that we would want to use as an example. Okay, the moment you say the term ignore effects of air resistance, that has implications as far as the type of motion that the object undergoes. So we have a scenario here without concentration on the actual questions. Let's understand the basics. If you throw an object up, okay, that object experiences the force of gravity only. It slows down uniformly. Hence, we are saying that the acceleration remains constant. It reaches the highest position and then moves faster and faster going down. Now, in both cases, the object experiences a constant acceleration because as it slows down uniformly going up, it's actually accelerating downwards in the direction of the net force, which is Fg. That's one application of the Newton's laws as far as VPM is concerned. Now, speaking of graphs, which is very, very important, okay? The moment the examiner says air friction is ignored, let's understand that that implies a free-falling object, and that object is a projectile, okay? So in the case of that object which was thrown, it could be a tennis ball, it could be anything, all right? So that object is a projectile, we're fine with that, and we're saying that a projectile undergoes free fall, the acceleration remains constant. Guys, these are the key ideas that make up, VPM in this question. Now, let's say for argument's sake we were to consider a graph of V versus T of an object that is thrown vertically upwards, right? For the mere fact that the object changes direction, it means we would need the two quadrants. Now, if, say, for argument's sake, it could be prescribed, the object is thrown upwards, and then we're saying upwards is positive. So as it slows down, this object actually will get a graph of this sort. Now, I want you guys to pay careful attention to the length of time that it took for the upward motion. So the first part, if I say this is A to B, and then to position C for argument's sake, the length of time that it took the object to actually reach the highest position is shorter than the actual motion for the downward movement of the ball. Now, this gradient of the graph, that's another mathematical skill. We also spoke about y is equals to mx plus c earlier, right, to say there's a mathematical relationship. Now, the gradient in this case, which is actually change in velocity per unit time, is an indication of the magnitude of acceleration, all right? Now, you'd realize that because this is a linear graph, then the gradient is constant. Hence, we are saying that this object experiences a constant acceleration, right? Now, the examiner may ask anything based on velocity versus time, acceleration versus time, position versus time. So, but the understanding in terms of the uniqueness of the scenario is also very important. Say, for argument's sake, we speak of the acceleration versus time. We would understand that the acceleration remains constant. Now, in this case, we chose upwards to be positive. So we've got acceleration in meters per second squared on the vertical axis, and then we've got the time on the horizontal axis. Now, because we took upwards as positive, and clearly from this graph you can tell that this has got a negative slope, then our graph will be below, which will be negative 9.8 meters per second squared, and then we get a horizontal graph like that. The horizontal suggests that the acceleration remains, constant in both magnitude and direction. Donnie, over to you for now.
Thank you, Themba. Guys, we are going to take a quick break, but before we do, don't forget to hit us up on our social media pages. Just search for Was a Matrix, as well as enter that competition. Send us your questions and comments, as well as hit us up on our WhatsApp line. We'll see you straight after the break.